Okay, good. And my voice is apparently audible to you all, I hope. No
Yes,
problems. Okay,
we
good,
hear you
good.
perfectly. Just go ahead.
Perfectly. Thank you. So yes, thanks, Mirjana, for inviting me. Indeed, I've been a bit busy, but the pleasure is all mine. It's always nice to share experiences with these common tools that we are all planning to use. And as promised, I will present some thoughts and experiences of using BAG in the PhD work or with the PhD thesis. And before I start, let's take a look at what is the actual contents of the presentation. So, first, I will properly introduce myself in the introduction part, and then we move on to discuss how to write good generators with the BAG framework, or at least in my opinion, how that should be done. And then I will take a moment of your time to advertise the Sidekick, which is design verification environment that we use and develop at Alto, which is also completely open source and will supports BAG. And then we have some design examples to show, so basically how to use BAG in optimizing the post layout performance of circuits. And finally, some conclusions on the things that we discussed. And if at any point you have some comments or want to discuss something, just feel free to interrupt. Good. So first, starting with who am I? So once again, my name was Santeri Porrasma, and I received my Bachelor's of Science in Electrical Engineering in 2019 from Aalto University, and then Master of Science in Micro and Nanoelectronic Circuit Design in 21, also from Aalto. And I have been minoring throughout my studies in computer science. So the two things that have been close to heart for me always has been electrical engineering or circuit design, and then computer science. So basically, this might give a hint why I wound up working with BAG. But anyway, so I have been a doctoral candidate since June of 21 in Professor Jussi Ryynänen's group, which is the group responsible for conducting research in the field of microelectronic circuit design. And I have been working with BAG since the spring of 20. So I started doing my master's thesis with BAG, and then continuing shortly thereafter with the PhD work. And my research interests include, as you may have guessed, so programmatic IC design, talking about BAG amongst other things, and then A to D converters as well. Then, before I start the actual presentation, I just want to emphasize that I was asked to contemplate on the pros and cons of using the method for layout generation. So they may be somewhat, or the points that I present may be somewhat opinionized, and your personal experience may vary. Okay, but with that out of the way, I think it's time to start with the actual stuff. So let's try to kind of answer the question of how to actually write good generators with BAG. So in order to answer that, we need to think what actually makes a good generator. So in my opinion, first and foremost thing that you need in a good generator is that you need to exploit the framework somehow in order to achieve a good analog layout. So talking about symmetry, matching, reliability, etc. So all of the analog layout things you need to take into account while doing layout and how to achieve that with the BAG framework. Then also some important things. So you probably want to exploit the underlying technology to its full extent. And then you also need to consider how reusable the generator is. So as you may know, it takes some time to write the generators. So you need to kind of contemplate that whether it makes sense to write generator for a specific application, especially if it's not reusable. But now, based on these points, I would personally say that in order to write good layout generators to begin with, you need to understand and know the framework that you're working with, and understand what makes a good analog layout in general. So basically, you need to, when working with BAG, you need to obtain a skill which kind of translates the different framework helper functions that are available to an analog layout which offers you good performance. Then some other things that you need to take into account. Well, first of all, you need a working technology definition, which is typically the hard part of creating generators or the workflow in general. I guess for most of you that are in the bootcamp, this is already provided for you, so you don't have to worry about the technology definition, which is always nice. But and for obvious reasons, we cannot really discuss the details of that. But it's typically, if you start writing the technology definition, you may have to reiterate a couple of times to get the parameters correctly. So that is one thing that takes some of the time in developing the generator workflow. Then one additional issue is that once you start writing the generators, in my opinion, you need to fix the topology before you start writing the generator. So you need to kind of know what you are doing in a way. So basically, what I want to say is that BAG is really not suitable for iterating the topology of layout. So you can iterate the layout parameters if your layout is scalable with that respect, but topology iteration is time consuming and difficult. So what you might actually do is if you are unsure about the topology, you kind of make custom layout, hand-drawn layout, a couple of topologies, and find the best suitable topology for your application, then write a generator if need be. And the last thing that you will need lots of it. So time is one thing that is certainly required once you start writing the generators. And hopefully that time investment that you eventually put into the generators is paid back if the generator is repurposable somehow. So you can hope to use it across multiple designs. Good. So now focusing on the how to kind of translate the framework helper functions to a good analog layout. So first of all, you have to kind of understand, or at least in my opinion, it is so that the learning curve for the framework is somewhat steep, and to this day, I still manage to find new and better and exciting ways of implementing the generators using the framework. So there are a lot of things you have to learn and take in, and it doesn't happen overnight. So you have to kind of reiterate your experience. But I would say that like starting to learn the framework, and it can be made easier. The learning process can be made easier by starting in the right place. So preferably if you have a working example, you can start with that. So I guess for the bootcamp, you have working examples where you start, which you can start to modify. So especially if they are using the analog base class, analog base templates, it is the easiest approach in my opinion, since it is the highest level of abstraction, in my opinion, that is available with BAG in general. So those are really useful for learning the basics of routing the instances and the transistors. And then once you have, sorry?
Could you elaborate a little more on why you say that's the easiest approach? I mean, have you tried using Lego or Lego 2?
Yes.
Or tried to reuse P cells, for instance? Let's say you have existing P cells. Is that still the case?
Yeah.
For
Okay.
the primitives.
So yeah. Okay. For Lego, I have no experience of Lego, so I'm not really sure about that. It might be that it's more easy to start with Lego. I don't know. So I cannot really say about that. But for the vendor P cells, so if you want to reuse them in the layout, you need to create pins on top of the vendor P cells that are on the grid. And I would say that like starting with that is probably not the easiest way of learning, because you really
sorry.
Yeah.
Sorry to comment. Like, was the question using P cells in general or using P cells inside bag or?
Yeah, reusing P cells as the primitives within a generator.
Within a generator. Okay, then Santeri, go on.
Yeah. Okay. Yeah. So as I was saying, so if you have those P cells and they don't have, or you need to create the pins in order to use them in bag. So I would say that like starting with the working example first to understand how the gridding works in general is a better approach, in my opinion. I haven't tried other approaches, so I don't know. I mean, I personally started with creating the P cell pins on top of the vendor P cells, and in my opinion, like going with analog-based working example and starting to understand from there is easier. But as said, your experience may differ. This is not the absolute truth, so to say.
Yeah, why do you think it's easier? I mean, why is that easier? Yeah, it seems like more work if I just look at it.
Yeah, well, simply due to the fact that the abstraction level is higher. You don't have to necessarily take in all of the details at first. So you start with kind of high level functions that create the routing. The grid is already there. You don't have to worry about that. So I think that is just like the soft landing the bag. Use the analog-based working templates to learn how the grids work, and then you can try to adjust the grids there and see what happens. I hope this conveys the message.
Okay, so your point is that the routing grid depends on using analog base, right? So because you want to use the routing grid, you also need to use analog base to design the rest of the primitive, right? Is that what you're saying?
Well, not really. So if you have this vendor P cells that you plan to use in your layouts, you can also create the grid without the analog base. Of course, the routing grid for a given technology, it will end up being the same as in analog base. But what I'm saying is that you can use the analog based templates as a kind of intermediate step between the like learning the initial things of routing, let's say.
Okay, so you're just saying it's easier because there's already existing examples, so you think it's easier to learn.
Yes.
Okay. All right. Thank you.
Good. Okay, so moving on. After you have learned the initial steps, as we just discussed, then it might be kind of a good step to make your own top level template where you combine the instances and then try to learn the placement, so how that goes. And while you are going through this process, it's kind of important to read, of course, the framework documentation. The documentation is not by any means perfect, but it offers you a kind of overview of what functions are available in the framework and what sort of functions you may use to perform different things. So even though it doesn't offer a comprehensive user guide, you get an idea of what's available, and then you can try different things in your layout generator. So that is kind of a must that you have to do. Okay, so now once you have learned the framework, which typically takes some time, then it is relatively easy to write generators with kind of, let's say, mediocre performance or good performance. But then if you truly want to try to squeeze that extra 5% out of your circuit, you really want to try and contemplate on how to solve the different analog layout problems, such as symmetry and matching and reliability and compactness of your layout. And
you said 5%, 5% area or performance, or what do you mean by? You said something about 5%, but you weren't.
Yeah. So yeah, what I'm referring to is that if you have, like, let's say with BAG, you might end up in a situation where you have extra space between the instances due to some technological like the gridding and so on. So what that translates to is extra area.
Okay.
And if you want to squeeze it down, extra area means extra power consumption and less speed and so on. So if you want to squeeze that down, you really have to kind of learn how to use the framework properly. That's what I'm referring to.
Okay, thank you.
Yeah. So yeah, let's discuss these individual points. There are, like, in my opinion, some problems, but nothing you can't really get around once you know how the framework works. So let's start with symmetry and matching. So symmetry, in my opinion, at least instance-to-instance symmetry is relatively easy to achieve. So that is basically just controlling the spacing and orientation of the instances with the framework, and that is basically really easy. So you calculate the coordinates and specify the instance orientation depending on the topology. So that is relatively straightforward. And then what is also an added benefit of the routing grids that are inherent to BAG. So the gridding is enforced, and that means that drawing equally distributed wires becomes a very trivial task. So that is just specifying a track ID with the certain pitch and count. And now this also boils down to the technology things. So typically I find it so that, of course, you should set your grid spacings and widths to be to the minimum of the technology. So that leads to more compact layout, of course. But then if you need more coarse gridding for some reason, then you need to learn how to set up the template grid on template basis. So in each of your sub-generators, you need to create a different routing grid in order to have more coarse gridding, so different spacing and different width. But that is one of the things that we discussed with the PSLs. So you have to also learn that at some point, in my opinion, to get kind of decent layouts. Then the matching concerns. So for especially when we talk about analog base, I think it's rather versatile in its support for many circuit structures. So you can easily code in amplifiers, current mirrors, logic gates, whatever. Those kind of regular structures are inherently supported, of course, by analog base, which is really nice. So you have a way of realizing those structures. But then if you truly want to get kind of good matching performance, you may have to get creative with analog base to achieve that, or with the framework in general. And I think this is best exemplified by an example that I have on the next slide. So we have think about an example case for, let's say, common centroid layout of current mirror. So first of all, we start with the kind of schematic representation of the structure, where we have the input transistor A and then output side transistor B. And then what I typically do when tackling these kind of problems is that I form a mental image of the layout, which is here. So basically, if you want good matching, you should have this interdigitation pattern in order to achieve maximum dispersion in your transistor array. Now, here you see that the first transistor for the first row would be A, and then we have two B's, and then A is the final transistor, and the pattern is basically inversion of that on the next row. And the first terminal for each row would be drain, and then the source is shared, and then the drain is common for both B transistors, of course, and then for the A once again the drain is separate. And now the question is that how do you actually realize this? Now this is also one of the things that might be kind of technology dependent, but at least in the setup that we are using, it's not possible to draw these MOS connections using draw MOSCon with one finger only. So you have to draw at least two fingers at a time, and that creates a problem here of course. So you have to kind of separate out the drain contacts for each transistor. So first thing you have to notice that I think in analog base by default, the first contact, depending on what comes before the transistors, you have to know that the first contact is assumed to be source. So if it actually is drain, then you have to swap the contacts that the draw MOSCon will return to you. So you call your source the drain, and vice versa for the source. So source becomes drain, and then after that, you for each of the rows you start calling the draw MOSCon, which returns, as you know, a dictionary of the different contacts that it is drawn. So source, drain, and gate. And each of those contacts is represented with single track ID. So basically you have to separate out that track ID into different wires. So you basically create a list where each element represents each individual drain wire. And then you have to start separating out the individual drains based on the topology that you have. And this way you can create kind of common centroid with the analog base, which I believe that, or at least I haven't found a way to make this like it isn't inherently supported, if I am correct. So you kind of have to perform this hacking to get it working. And then of course, depending on the number of dummies you have on each side, you may have to fix the schematic generation if the dummy terminal labels are not correct. So you may have to take care of that, but that is also relatively simple to achieve. Then after the matching things, reliability is also one issue that I would like to address. So basically, the technology definition handles it should handle automatically this wire width versus the current draw, so the EM specs. Of course, you have to take care to call the correct helper functions. So you know that you have wire with certain DC or RMS current. So you have to take care that wire width follows the EM specification of your technology. And that is somewhat automatically handled, or the calculation is handled by the technology definition, which is nice. You don't have to take care of that, the nitty-gritty details. But then when it comes to the number of vias, it is sometimes difficult to get what you want exactly. So basically what the framework does in the background when creating vias is that it tries to maximize the number of vias for a given connection and a given technology. And this is true, once again, we come back to the technology definition. So this is true only once the technology definition is correct. So you have to enumerate basically every possible via parameter combination for your technology. Well, not every possible, but you have to have the certain rules there in order to make nice vias. And in some situations, it can be that the interconnect resistance is actually dominated by the vias. And if you don't want to increase your wire width, you have to once again resort to hacking the framework somehow to get the number of vias up for your connection. And once again, we have an example of this situation. So basically, here we have two different wire arrays, wire array 1 and wire array 2, that we want to connect together. And these are now on adjacent metal layers. So what you would typically do is you would call connect to tracks and supply the wire array that you want to connect, and then the track ID you want to connect to. And the framework certainly, it calculates the bounding box of the intersection and checks whether it can fit vias there, and automatically places the maximum number of vias in order to minimize the interconnect resistance. But then, as said, typically with the minimum width wires, and depending on technology, of course, it might be that the via resistance actually dominates, and you want to have more vias. So what I have ended up like doing in some of my generators is to write a helper function which does the exact same thing as connect to tracks, but it takes a couple of different arguments as well. So you can specify the extension direction that you plan to extend to and the number of vias. And based on the technology definition and the number of vias and the extension direction, and the available information from the wire arrays, you can calculate a bounding box, new bounding box for your vias, and have multi-cut vias there in order to minimize the resistance. And as you can see, for instance, in this example case, the via resistance would be reduced by a factor of 3 by using this approach. On the other hand, this creates some problems, as you may imagine. So if you have wires on same layer as wire 1, right near to this wire array, and you try to route over this wire array 2, then you will short out the wires, and you have to kind of manually take care not to do that. And of course, the framework has convenient helpers for checking that whether you can route to this coordinate using some certain track. But yes, so in order to minimize the interconnect resistance, you may have to resort to these hacks, and then you may create more problems than you eventually want, and you have to ensure that you don't get the shorts there if that happens to be possible.
So where did you define that connect helper?
Well, I think we have collected the kind of technology independent helper functions under back to methods of the MOSAIC project that is available in GitLab, I believe. I'm not sure if I have transferred actually this connect helper to there, but the place
Where
to
is it
collect.
currently defined? Is it a part of that generator you're saying?
Yeah, it's. I think it's
You're saying
currently part of my generator. Yes, but that
So
could
you
be
think it
made.
should go into helper to methods, right?
Yeah, it could be transferred there. Yes.
But okay. So why there instead of back into the original framework? Just because it's easier to
Yeah,
merge
well,
into?
that is also a good question. So why not instead of the original framework? Well, I would say that there's a certain reason not to touch the original framework. I mean, like you shouldn't. If you can make a helper function that solves some specific problem, but then with this, for example, this specific case, it doesn't ensure that the routing always goes correct. So you have to make sure that you don't short out when you extend into the X direction using a metal layer that is originally routed in the Y direction. So I don't know if that's kind of a good fit into the original framework per se. I don't know.
You're saying it's too much of a hack to move back into the original.
Yeah, maybe so. Maybe so. Of course, we could
Okay.
try to make merge request to the original framework, but yeah.
Okay, thanks.
Okay. Then the final thing that I would like to discuss is the compactness of layout, and this is a hot topic, at least in our lab. So I constantly hear these comments that, hey, your layout is looking very sparse. So there is space between the templates, and that is typically due to the way that the layer generator, the way that analog base handles the spacing between the transistors and the substrates. So basically, I think analog base, what it does is it automatically tries to add some space between the transistor rows and the substrates in an effort to center the instances or the instance Y center coordinates to the grid. And now if you have freely adjustable transistor and substrate parameters, this will typically fail. So the substrate track will not be typically centered with the substrate diffusion Y coordinate center. And the end result of that is that the substrates are not symmetric with respect to the Y coordinate center of the whole template. And now if you try to overlap substrates from similar cells, it will cause DRC errors. And if you don't overlap, the layout will be more sparse and you will suffer a penalty to power consumption and area and speed. So basically this example here illustrates the problem in more detail. So let's imagine that we are working with the inverter template, and we have top level generator where we, for some reason, we want to place two inverters on top of each other. So how you go about that is you call add instance on the inverter master and specify the location and then the orientation of the devices. And now if you specify the second inverter, so the one that is on top, you specify that Y coordinate with the height of the bounding box of the inverter master, then you will end up with this empty space in between the substrates. Notice how this instance is oriented in MX orientation. So basically it means that this substrate and this substrate here could be overlapped in order to conserve area. So now if we move this instance that is on top down by this amount diff, that is the difference between the Y center coordinates of the substrates, we will end up in this situation where we get this via collision and DRC errors, depending on your technology, of course. And now, once again, you have to start to understand how the framework actually calculates the substrate location. So you have to know what in your technology specifies this distance between the y0 and the bottom coordinate of your substrate. And then once you know that number and add that to the half of your substrate height, you can always round that up to the track pitch. So basically changing your substrate width to center the track. Then if you do that, you will always kind of guarantee that your substrates are symmetric with respect to the template, and you can overlap the substrates and save some area there. So once again, it kind of boils down to the understanding on how the spacing is controlled there, and what you need to take into account once you start squeezing the layout area down. And there's an argument saying that this is not the spacing there that originally exists is not too significant, but of course if you start to build massive systems using these analog-based templates, then of course it starts adding up, and it will mean that you consume extra power and suffer a penalty to the area and speed of your circuit. Okay, so those are my.
Are you saying that it's not possible to overlap those the substrates? Like, because if you overlap them correctly, the vias should be right on top of each other, right? Are you just saying the framework isn't going to do that alignment correctly, or are you saying there's something else that's keeping it from working?
No, I'm not saying that you can't. So what I said is that you truly have to take care that your substrate width and the parameter that controls the spacing here, so that the sum of those two is divisible by the track pitch. That way you can overlap the substrates. So you have to kind of, what I wanted to convey is that you have to understand how the spacing of the substrate and where the substrate is placed in the first place. You have to understand how that is calculated. But it is certainly possible to overlap, and you should overlap the substrates if at all possible to conserve area.
Okay, can we, sorry for interruption. Can we put an option to remove this substrate contact from one P cell? So we don't need to overlap because we have already one row. Did you get my question? Because now we have two different instances. One has P tab and the other one also has P tab. So we can put an option to remove one when we calling this function. So we don't need to overlap. We have only one tab contact or well connection.
Yeah, I understand. The only problem there is that if these are individual templates and you run LVS on that, then it means that the P substrate for your other template is kind of floating since there is no substrate contact. But on the other hand, yeah, if those two are kind of constructed in the same analog base, then certainly it would be possible. But at least I haven't found a way. I think the analog base doesn't like directly support placing it just places the substrate rows on top and on bottom, and you cannot control where they go. Okay. But adding support would be nice.
I think you can leave it out, but and the problem that you mentioned with the LVS is that if you run hierarchical LVS, then you're like top level design which contains these two instances. The other one won't be clean. The layout is different. But I'm not absolutely certain about this. It's how the hierarchical LVS is actually run. Yeah, but adding the option is a good idea. At least it could be tried.
Yeah. It would be nice to have the ability to control where the substrates go. in the analog-based templates. Yes. Okay, so just to summarize the experiences in a couple of words. So overall, I think the framework is easy to learn in quotation marks, but difficult to master. So what I mean by that is that once you get past the initial learning curve, it is easy to write generators, perhaps with mediocre or even good performance, but then it's more difficult to kind of squeeze that extra 5% performance using these hacks. So you kind of have to hack the framework in order to get the desired outcome. And yeah, that means that you truly have to understand what goes on in the background in the framework, so how things are handled there. And sometimes when you start creating these hacks, then it means that you have to take care of some other problems that might appear when you start hacking. But I think my advice for learning bag, I would say that, like, don't worry about writing mediocre generators when learning, or don't worry about the outcome. You are kind of learning, and once you are more confident with the framework, then you can start to optimize the performance and optimize the layout, so to say. But yes, that kind of summarizes the experiences, and now we are moving on to the design examples portion of the presentation. And before we go there, sorry?
Do you find that you can maintain process independence even with hacks? Like, when you add a hack, is it going to break process independence? Or
that's an excellent question. I really cannot answer that because I don't have access to I only use one process, so I wouldn't know. But I guess we would have to test different generators with different processes in order to fully answer that. And yeah, it's a difficult question that I don't know the answer to. I am sorry. I'm sorry, but
okay.
Yeah.
That's a good answer.
I could probably say that most often the situation is, as Santeri describes, the one who writes the generators is only one process. And my advice would be, as Santeri's advice for writing these mediocre generators, that don't worry about it, it will be eventually solved by someone.
Absolutely. Okay, so yes, before the design examples, as mentioned, I will take a couple of minutes to advertise the Sidekick, which is a framework, design verification framework that we use at Alto, and which we are developing. So active development is happening, and we hope to have more contributors, of course. So that's why we try to advertise it a little bit. So basically, real quick, the idea of the Sidekick is demonstrated here with the block diagram. So what the Sidekick is as mentioned, it is a methodology for design verification, and it is also based on the Python programming language. And the Sidekick itself consists of interconnected Python modules that are called entities. And these entities are models for your circuit blocks, and the model abstraction level can be controlled with a single parameter. So for instance, you can have a circuit block, let's say an amplifier, and you can have a Python model for that. And then you may wish to define some simulator calls, so you can have a real analog hardware model, which is represented with the analog netlist that you get from your netlisting output. So that would be kind of Spectre or Eldo model, so to say. So you can run Python model or analog model, and then what is nice that you can control or connect individual entities together to form a system as a whole, as is illustrated by the middle block here. So the system consists of several hardware or circuit level blocks that are connected together by their inputs and outputs. And since it is possible to control the abstraction level, it means that you can run kind of design verification from high-level system modeling with Python up to verification on silicon. So you can also control measurement instruments through the Sidekick. And some features that I want to elaborate. First of all, the entities have a minimum set of constraints. So basically, you only have to define the input and output definitions for your entities, and that is in order to establish an interface using which you can connect that entity to other entities. And moreover, the entities have to obey a consistent file structure. But I think the main benefit of the Sidekick is that it tries to, as well as possible, automate these repetitive and well-structured tasks that are related to IC design. So you generate the simulation test benches automatically, and you handle the simulator calls automatically. And recently we have been working on an interface for parasitic extraction, net listing, and LVS. And then also you can write different entities for post-processing. So what we have implemented, Bode plots, frequency domain analysis using the signal analyzer entity. So basically FFT of your transient output. Then time domain analysis as well using the oscilloscope entity. Currently we have support for a couple of hardware description languages and QuestaSim. And then also from the analog side, we support Eldo, Spectre, ngSpice, and recently I think ADS Momentum has been added to the supported simulator list. And as mentioned, you can control the measurement equipment as well if you have the drivers. And perhaps more interestingly, in context of this presentation, Sidekick is BAG2 compatible. So you can set up your Sidekick entity to use the bag generator that you have coded, and then you can run layout sweeps for that generator, which I will demonstrate in a short while. But if this spiked your interest, please go check out the webpage. The link is there. You can also Google the Sidekick and GitHub, and I think the first result should immediately take you to the correct place. Good. So moving on to the design examples. Okay, I'm a bit short on time. Let's try to wrap up real quick. So the design examples, as said, I have used some of the generators that I have coded together with the Sidekick to perform some post layout sweeps and try to iterate the performance by using different layout parameters. So first example case is ADC input buffer. Here we have pseudo differential input buffer using the source follower topology. And this generator doesn't use analog base per se, but it uses the vendor provided device generators, which have the pins created on top of the existing contacts there. And the passives are done using the vendor provided device generators as well. And then what is certainly nice, as you can see around the device, we have, sorry about that. Around the device, we have automatic filling with decoupling capacitors based on the target area using the vendor P cells. So that is certainly nice, in my opinion.
So what's generated?
Sorry?
Sorry, you're saying, I mean, your bullet points here tell us what was generated using vendor device generators, but what was generated using BAG? or
everything. So bag kind of controls the vendor device generators in the background to generate the instance, and then using bag you generate the routing and placement and yes, everything is generated in bag, but you control the vendor P cells using bag.
Okay, so why don't, I mean, earlier you had said that you recommended starting with XBase for that part of it, right? And then I guess why don't you recommend this method here?
Yeah, so as I said, it might not be, in my opinion, the easiest way to start learning bag, but if someone feels that they would like to start by creating the pins on top of the P cells and go that route, that is perfectly fine. But my personal opinion is that I wouldn't recommend it. It is. I think it's just a matter of opinion.
Examples?
Sorry?
Because there's not as many examples, or why?
Well, basically, yes. I think I'm not sure what kind of examples you have available, but in our lab we have many working examples of analog-based templates.
So this is the only example of this one, or do you have other examples of doing it this way?
Can I maybe dig in? I'm sorry to interrupt, Santeri.
Yes.
Can I take over? So my view on this is the following. In order to enable this, like, let's say, methods, you need to change the analog base, and you need to clearly understand how to like instantiate from bag vendor like provided generators for P cells. And that cannot be shared because it is technology specific.
Yeah.
And in a sense, the only thing that can be open is like these, like rectangles and initial analog base. I will think about that, because even if the methods are shared, there is some part of information that never at this like current standing with the foundries can be shared. So maybe that is the reason. So Santeri, please correct me. I probably am wrong, but I will see that as the way why to start with XBase, because this approach cannot be shared from one institution to another without NDA signed between that institution, Alto, and TSMC.
Yes, that is certainly one of the key reasons. I would say that you really cannot share those technology dependent things, which makes like providing working examples also very difficult. Yes.
Okay, so when you did this one, you didn't have any inherent problems with the P cell, for example, like callback issues that prevented you from doing this, right?
I did. I did.
You did. Okay.
I had to change. I had to kind of change the skill code that is included in the framework. I think we did a merge request to the original framework to fix some of the problems. It was a really simple fix in the end, but I don't remember exactly. But it was related to the callbacks, as you said.
It was merged, and it's part of the MOSAIC back framework at the moment.
Okay. Yeah. I hope this provided a satisfactory explanation as to why I wouldn't recommend going with the P cells instead of analog base. But yes, I hope we can now move on. So yes, so for the input buffer, here we have a sweep demonstrating capabilities of just kind of iterating the post layout performance until you reach some desired point. So let's say that we have a situation where we have initially designed the input buffer, and we have wound up with some transistor sizing, and we have an input transistor multiplier of 8, and okay, we simulate and extract simulate with parasitic extracted and we see that okay, the linearity is actually limiting performance. Then we start to think that okay, we want to perhaps get the linearity to the same level as the noise without sacrificing any bandwidth. So basically, we start increasing input multiplier, and then we can simulate some steps in between, but yeah, basically multiplying the device dimension by 2, we see that okay, we approximately reach plus 6 dB linearity and end up in the situation where the noise and non-linearity are approximately in the same level. And in my opinion, this nicely demonstrates the capability of using bags. So you can already include kind of post layout parasitics in your sizing loop, however you want to implement that. Then another example.
So it's scaled by the input multiplier. So you're saying
Sorry?
you just change. It's parameterized according to the input multiplier, your generator.
Every instance parameter is controllable, so everything is parameterized.
I guess what I'm trying to ask is like a high level parameter. Can I just say I want an input multiplier of 2 or 4 or 16? Because there you showed one with 8 and one with 16, right? So is that something I can just very easily, change a parameter and rerun it to get a different value or a different?
Yes, it is that simple. You only change one value. Yes.
All right, thank you.
No problem. Yeah. So okay, then next case is the n-bit IDAC. So this is actually not written by me. This is written by my instructor Marko Kosunen, but he has kindly given me permission to present this here as well. So basically, what we have here is a parameterizable current mode D to A converter. Everything is of course parameterized, but what is more important that the number of bits, number of outputs is parameterized. Here is example case generated with 5 bits. And as you can imagine, this is very useful circuit block for various circuits. So it is kind of reusable, and I think if I'm not mistaken, we have already taped out at least one chip with these generated IDACs. So certainly it is a kind of reusable block and very nice demonstration of these generation capabilities. And we have also built this kind of IDAC verification test bench using the Sidekick. So basically, in all simplicity, what it does, it drives through runs through the code space that you have in your DAC. So inputting each different code and recording the output current based on the code, and then sampling the output. So here we first figure we have the transient output, and then we have the kind of sampled output from the transient one, which demonstrates nicely the input to output characteristic of the DAC. And then we have also a method for extracting the INL and DNL directly from that. And this is nice. You can change single parameter, ask how many bits you want in your IDAC, and generate automatically the characterization results of the IDAC as well. Then next.
Is that example online?
No, sadly no.
So could we see how you use Sidekick here to do this somehow?
I think in the current state not. Sorry. We would have to clean up.
We need to book a different session for that. This IDAC generator is the one that I was showing you in the previous meeting. So yes, we can demonstrate how to use it, but in order to publish it, we need to clean it up.
Yeah.
Because there's proprietary information, or just because it's needs to be improved?
I think that there is a danger that there is proprietary information there, so we cannot show it immediately.
We need to clean up the commit history,
Yeah.
basically, and probably add some documentation. But cleaning up the commit history from the proprietary information is the one that we need to do. And in order to make this useful for everyone, we should test that it works also with the Cadence CDS FFmpeg process. So we haven't tested that with that. But we can give you a demo how it is constructed with the current process setup, because during that demonstration you don't see any proprietary information, I guess.
Okay.
Yeah.
Good. Okay. Moving on. I'm sorry. I feel that I'm already over time, so I try to go real quick.
No, take your time. Take your time.
Yeah. So the next design example that we have is a low voltage cascode current source. Basically, utilizing the IDAC in the layout for a tunable input reference, which we see here, and then on the bottom we have the cascode current source itself, and of course every imaginable device dimension is parameterized, and we have optional software flag to toggle on and off the generation of the RC low pass filter in the current mirror. And what we have done here to illustrate the generation capabilities, we have tried to sweep the channel length for the mirror transistors in order to find certain output resistance level. So basically generating layout with different channel lengths, and then recording the output current versus the output voltage, and then extracting the output impedance from there. So with this, you can search for the output resistance level that you want, and try to see what the circuit area is. Of course, that those two are kind of trade-offs. So with higher output impedance, you have more circuit area. Yeah, but this is used for the next design example, which is kind of a this is pseudo differential voltage to time converter, and this is one example of kind of a let's say higher level generator, which utilizes more of the sub-level generators. So basically sub-generators or individual generator blocks, and places them together. So in the layout, we have the cascode current source, then bootstrapped switch generator, then we have some transmission gates and inverters there, I believe, yes. The operating principle, real quick, if you're not familiar with V2G conversion, basically there are two clock phases. So in sampling phase, we sample onto the sampling caps, and then in the opposing clock phase, we start to discharge the sampled analog voltage using the constant current source. And then once the voltage level over the cap goes over the inverter switching threshold, the stop signal is asserted, and hence as you're discharging with constant current, your rising edge location in time is directly proportional to the sampled analog input voltage. And this generator we have used to demonstrate the kind of noise and linearity optimization. So there is a trade-off between the two, so to say. So we have swept the VTC integration capacitor and the current source output mirror ratio. So this ensures that the voltage to time gain is constant. So you always get the same range in your output signal. But then the SNR starts to increase as you increase the integration capacitor. But on the other hand, you increase the output mirror ratio, then the SFDR or linearity in general starts to go down. And here we can see that okay, we have reached certain optimum in SNDR at around mirror ratio of 4, which is nice.
Sorry, so
Yep.
When you say you swept those, you mean you actually use the generator to get post layout results? So these
Yes,
are your
all of these,
post
all of
layout
these
simulated results, right?
Yes, all of these results that I showed you are post layout. Yes.
So you extract it, so you change the parameter and had the generator regenerate and extract it and then give you these results, right?
Yes, yes.
Okay. Or it looks like two different generators, one at 4 and one at something else. I guess it doesn't really say here. What were the numbers?
The generators are the same, but what the numbers mean, so it's mirror ratio, and that means basically the yeah. Okay, you got the point.
Yeah, okay. So yeah, you did, it looks like you did 5 different ones then, right? So
Yeah.
it created 5 different layouts, right?
Yes, with the generator.
Each got extracted. So are you able to run all 5 at once? Like if you were to make a change to the generator and then you just tell it to run, it'll run all 5 and give you the results, or you have to run each individually and then compile them yourself?
Up until recently, we had to run the generators like one after the other, like run generator, extract, simulate, and then do the same thing again, like consecutively. But recently, I found a way to enable parallel generation, extraction, and simulation of the different test cases. So they can be run in parallel as well.
Okay. All right. Cool. Thank you.
Okay. Yes. Sorry, I'm a bit over time. Time to conclude. But what I want to say about BAG in general, and summarizing my experiences during these past 2 years, I would say that BAG is extremely versatile. So talking especially about analog base, you can code in many different circuit structures, and it is, once you get past the initial learning curve, it is very easy to use for mediocre quality layouts. And then in order to take your layouts to the next level, so get good performance, you have to typically start hacking the framework. And once you start these hacks, then some solutions may indeed cause more problems, but then you have to simply take care. You have to be extra careful when you're applying these hacks, so you don't break anything. Then I guess the burning question, like summarizing everything now together, is it worth writing a generator for application X, so some unknown application? I would say yes, provided that you need to either reiterate the layout parameters in order to reach the desired performance, or if the generator is reusable. And the thing is that sometimes, or even typically, you end up reiterating the layout parameters, so you might as well make the generator in the first place. But yes, I think that is all I wanted to say. Questions and comments are welcome if you have time.
Okay, people from the audience, please.
Yeah, I think
give it a shot.
Oh, can you hear me?
Yes.
Okay. Yeah. So hopefully we can hear a little more about Sidekick and how that works. I mean, I guess yeah, it seems like there's just a lot going on in there. I just wonder how it all works together, and it's kind of like BAG in some ways. Maybe it just I think we need a demo for that. So at some point here. So maybe we have to have a separate presentation, like Marco was saying.
Yeah, Marco, I think it's possible to arrange something like that at some point.
Yes, definitely we can give a demo. One thing I would like to mention that this modularity, like keeping the sidekick and the bag, how to say, separate, is intentional. Also, the methodologies that we have for example, like LVSs and stuff like that, they are separate from the sidekick, so they are. That is to maintain modularity. So we can give a demonstrate how we use the bag from within the sidekick, but basically how to use bag. That is just a demo how to use bag from any Python environment. Sidekick just happens to be one. It's a useful tool, but you can use it independently for all your design modeling, measurement, control, automation. So it per se doesn't have anything to do with bag. It just happens to work nicely to work together with. But yes, I can.
So why are they all together? Like, why don't you have a separate project for post-processing and one for, control, or kind of on different, they're distinct.
So why we have it? Was that the question? Why we have it separate?
It has a lot of features. Why are they all integrated together? Why aren't they separate?
For example, in the sidekick, the principle is that as we are building ICs, we eventually need to measure them in the measurement room, and we need to model the system in some way while we are developing it. So basically, throughout the design of that system, we are just running tests on the system, and like the system is built on principle that you have blocks that model hardware, but it doesn't take any stand on what that hardware is. It is just a block of hardware that can be connected to another hardware. So you construct your system model with that and run them together. So it's inherently, it's the core of the sidekick is the formalism of I/O definition of those blocks, and then you can model whatever with that. And we have coded their interfaces to most of the analog simulators we use, and that makes it possible to use analog circuit models as circuit models of those building blocks. And now, like, bag is just one source of those analog circuit models that can be used within the sidekick. So it's very modular, and that's one of its inherent strengths. You can do whatever with it. I modeled COVID-19 pandemic with a sidekick.
Okay.
Yeah. Good.
So one other question from myself, Florian speaking. So how much work have you actually automated the design scripts and design procedures? Or is it like manual tuning and you just regard it as a schematic and layout generator, you give it the dimensions?
Yeah, I think we haven't really made anything that would kind of like have any sort of automation in terms of the design parameters. So answer is no. That of course would be nice to start realizing at some point. So make some sort of an algorithm for kind of designing, relating the performance to the parameters of the circuit and trying to kind of automate the optimization. But as of now, it is in these examples that I showed you, it is more of like manual tuning, so to say, in the sense that you have a wisdom which tells you what parameters to tweak in order to get the performance to those levels that you want, and then you specify that, okay, run the layout generator with these parameters, extract and simulate, and then see what is the result. So there is no kind of intelligent control. You just have to provide the parameters yourself. but definitely interesting topic for future developments.
Okay, thanks. Okay, maybe follow-up question. How many parameters, just a rough guess, let's say the voltage to time converter has on the top level?
Oh, I think, yeah, I think it's about 500.
500, yeah.
Yeah, so quite many.
Okay, yeah.
500. Okay. What are, I mean, are those, how many of those are layout parameters, like directly affect the layout versus more schematic?
Oh, hard to say. Maybe I don't know, 10% or so. Maybe so, like 50. It's really difficult to say. I don't have a solid number, but definitely the schematic parameters take majority.
So which, okay, so which, why aren't those a part of the process definition then? Like, are those process specific then?
Of
Those
course
layout
not.
parameters?
Of course not. So layout parameters. What I mean by that is to, for example, control width of some routing or width of some pin or something like that. So I don't feel that they are necessarily like technology parameters, but rather kind of circuit dependent parameters.
Santeri, thank you so much. It was
Thank
very
you.
interesting presentation, and yeah, we're looking forward to the follow-up, because you are just at the beginning of your career as a PhD student. So maybe in a year you have more things to tell us, about the
Yeah, what are
back
you working on
framework
now?
and the hacks that you did.
Yeah, absolutely. The tape out is happening, and let's see, maybe we have more circuit generators coming up in the near
Yeah.
future.